Question 5. Consider the interconnection shown in this figure and what value of alpha is required to make this a valid interconnection. Very good. So as you see, we have an independent here, independent voltage source. We have an independent current source, and we have a dependent voltage source. But this voltage source is depending on a current. So we call this a current controlled voltage source. Okay, so this is a current controlled voltage source. Current controlled voltage source. Okay, and it's controlled by I delta, and with the coefficient of alpha. So the voltage here is alpha times I delta. Okay, sounds good. So we would like to pick a value of alpha such that this is a valid interconnection. Okay, sounds good. Let's clear this. So, okay, so I have a 6 volt here, plus minus 6 volt here, and this is exactly parallel to this. So therefore, if I call this, let's say V1, and if I call this V2 with the same direction that is shown here, and V1 is going that way. So hopefully everybody agrees with me that because V1 and V2 the signs are different, polarity, the reference polarity are different. So V1 is negative of V2. So if we learn KVL later next week, we're gonna also, we can do the KVL here and say negative V1 minus V2 equal to 0, which we're gonna get the same thing. But for now, because we haven't learned KVL, it's just a simple parallel case. And because polarity is different, so they are basically negative of each other in terms of just the reference. Of course, both of them are 6 volts, like from this point, if it is A and this is B, V of A minus V of B is 6 volts. But the matter of the fact is that V1 happens to be VA minus VB, 6 volt. However, just was because of the reference V2, I defined V2 to be VB minus VA, which is negative 6 volt, okay? So we have that. Very good, so I would put V2 equal to negative 6 volts. Somewhere here, V2 is equal to negative 6 volts. And okay, so that has to be equal to alpha times I delta. So as you see, that voltage V2 is equal to alpha times I delta, and has to be equal to negative 6 volts. So what is I delta? I delta, okay, that's also interesting. I delta is this way versus 15 amp is this way. So 15 amp is going, 15 milliamp is going that way. So I delta is in a different direction. So therefore I delta is negative 15 milliamp. So I delta is negative 15 milliamp times alpha equal to negative 6 volts. So from this, alpha equals to negative 6 divided by negative 15 milliamp, which is, simplify this, becomes 2, 5, and then because we have milli, let's say it comes up, this, 2000 divided by 5, basically, volt per, it is 400, okay? 400. So this is alpha. The alpha is 400 volt per amp. So with this value of alpha, Then you get exactly the voltages are matching, and that's the only thing that we have to basically check. Okay. And here we don't have to be worried about the currents because there's only one current source, and whatever amount is going to these voltages, it's fine. There's no restriction on that. Okay, so the part okay, so part A we are done. What value of alpha? We find alpha is 400. Part B, for this value of alpha, find the power associated with the current source. Okay, so let's do that. So save some space for that. So basically, we want the power for this element. If we call it element 3, I want to calculate P3. So let's do this. We can just assume some reference voltage and current directions, and let's do that. But if it is me, the way that I would do, I would just look at this. This was 6 volts, right? So therefore, this is also 6 volts. So the voltage would be 6 volts. And then the current that is going exactly this way, from plus to minus within the element, which is complying with this 15. So this is 90 milliwatts. And it's positive. So it means that actually it is absorbing. Current source absorbing. Okay, great.